Swayam Prabha. Digital India. Educated India.
So we started off with ethane and then now move on to propane and then butane and so on. Let's see how far we can go. So when we are talking about propane, it is, the general formula is CH3, right? So if you look at either this bond, this carbon has one methyl. If you look at this part of the carbon-carbon bond, then again this carbon has one methyl, right?
The molecule is symmetrical, sir, so it doesn't matter which way we take the compound.
Yeah, in this case it doesn't, right? So if you are starting off with this, let's say, if you want to compare this structure with this structure, what this structure represents is, okay, one of the carbons, hydrogen, is now substituted with the methyl, right? So we can rewrite this structure. So I am doing a simple small modification. So we put this as, correct? So in this Newman projection, this is the Newman projection for propane, N-propane. Similarly, a staggered conformation of this would keep the methyl in between the hydrogens, right? So again we can keep the methyl here, which again keeps the methyl between the two hydrogens, right?
Now the angle would be 60.
What?
Will the angle still be 60?
Yeah, well, the angle will still be 60 degrees. Angle will still be the 60 degrees. But what you have to pay attention to is, what are the additional factors that has come into the molecule other than the simple torsional strain or the bond pair repulsion that you had previously. What are the other factors that you have incorporated? Steric. Steric due to? Van der Waals. Steric due to what? The hydrogens of this CH, hydrogens of this CH from the methyl. Methyl CH, this methyl CH, alright, and then the behind carbons hydrogen, right? Those two, if you have a connectivity, let us say write it little more. So you basically have 1, 2, 3 CC, right? 4 bonds, and atoms, if you count 1, 2, 3, behind carbon 4 and the hydrogen 5. So now you have started to bring in the steric aspects into the molecule other than the torsional strain, right? So what was the torsional strain previously? It was between the bonds, which is CH and CH, right? Now what are the torsional effects possible here?
Sir, I have a doubt, sir. So you said that it would be 60, sir. Is there any fixed reason?
No, we are measuring the interactions at 60 degrees.
At 60.
At 60 degrees.
At staggered with
This is the least. This is the center where you can have least interaction because it's the midpoint of, right, these two hydrogens.
But
So
sir, can't we say that since CH3 has more hydrogen atoms than that H over there, it should repel more than that singular H, sir?
where else you want to place it, you would place the methyl, let's say like this in an eclipsed form. There we will have maximum steric. You keep it away from this, little more away. Again here, right? That's the midpoint. You call that as staggered. So you have moved it to 60 degrees. You have rotated it to 60 degrees. Further rotation would again bring it to eclipsed.
Yes, sir.
Again you will start the maximum interactions of steric coming into picture. So the minimum point or the minimum energy point at which you will have the less sterics is here at 60 degrees.
But also, sir, can't we also argue that CH2 and the other H, sir, they will also face steric hindrance?
Which CH2?
The CH2 and the other H, the other side.
Yes, this will. To simplify this, I have shown it like this. Actually, you have 3 hydrogens attached here. Right? So this methyl will always be rotating along its axis. Right? So at any given point, this hydrogen would meet this hydrogen, or another point you will have this CH interacting with this CH. Again, this CH will also interact with this CH. Right? But whenever the hydrogen, this CH and the methyl's hydrogen are coming in a way that they would hit each other or aligned this way, that is when you will have the maximum sterics exhibited. If you look at the solid state structure of this methyl, it wouldn't be facing, it wouldn't arrange in a way that these 2 hydrogens are aligned. They would keep the minimum. So this hydrogen would exactly sit between the 2 CH. Okay, you understand? So though it is in eclipse reconfirmation. In eclipse reconfirmation, this methyl's 2 hydrogen would keep this hydrogen between them. Right? That is the orientation. Now, if you just keep moving this methyl, shifting it to a staggered, and this is the minimum energy point where it will have least steric interactions. So that's why we are saying 60 degrees. Okay. So now this is the staggered conformation. How much would this? So you have brought in the steric component, right, along with the torsional strain. We are discussing about torsional. When compared to the ethane here, what are the torsional factors that are coming into picture? CC and the CH. You also have the CH and the CH. Correct? So in eclipsing interaction, you still have the hydrogen-hydrogen eclipsing, which is worth the value of 1 kilocal per mole, computed 1. And if you are calculating this methyl, right, contributing to this, it is close to 1.3 kilocal per mole. So you may assume how much steric has contributed? 0.3 or something. Right? So that is the amount that you can have steric interaction. Now, if you want to calculate the energy of this eclipse reconfirmation for a propane, yeah.
So is there a possibility where the steric factor overpowers the torsional one by a huge amount, where we just ignore the torsional?
If steric factors are becoming very much concern of a concern, let us say, this molecule would try to pull, the atoms would little stretch apart. Okay, so the bond length you would see that increasing. That is noticed, right? If you increase this bulkiness, let's say you keep tertiary-butyl group here instead of a methyl, right? That will bring it up, very huge sterics would come into picture, and you would see this particular bond would be stretched than that of a typical carbon-carbon bond length of how much? 1.54 angstrom or so, right? So you will see a slight elongation of the bond. Just to avoid that steric, the bonds would stretch. Okay, so you would see that. Now, how do you compute the eclipse energy? Can you do that? How many hydrogen-hydrogen eclipsing interactions are there? So here 1 kilocal, here 1 kilocal. You will add this also 1.3. So all put together, it will be 3.3 kilocal per mole. Right? In the case of staggered, so we know when H is staggered, the value was 0. Okay, it was 0. When methyl is staggered, the value is again 0. The value is again. Steric factor was made here. When it was away, it is minimized. Right? We already said, yeah. Someone is asking.
So is this steric factor due to the CH3 0 because it's being equally pushed by the sigma bonds or hydrogen on both sides?
Say it again, could you?
So is the steric factor, the net steric factor on the CH3 0 because it's being equally pushed by the hydrogen the bonds with the hydrogen on either side, which is the.
No, it is just that it is away, because in the ethane case, what we saw was in the eclipsed form, 2 hydrogens are separated approximately to a distance of 2.3, right? And in the when we move that from or when you rotate this carbon from a eclipsed form to a staggered form, the distance between the hydrogen becomes longer, little longer, and that is 2.5 angstrom also. Here also the same phenomenon occurs. When you move this methyl here, right, they are separated away from the hydrogen, and hence the steric interaction also comes down. The additional 0.3 or whatever we had the steric, that becomes completely null. It's equivalent to that of a hydrogen, that case. So you will have a 0 value for the staggered form of this. Yeah, here had a question, then I'll come.
So when we have some energy when we have tertiary butane instead of.
Yes, yes, the magnitude of this would increase.
So no sense, but zero will be get.
Oh, here, yes, you would see a big number. When you have 2 methyls itself, you would see.
We don't set that.
We will come to the butane stage. You will understand.
We don't set that as 0. Yeah, like because we set the for staggered it only CH3 twice.
No. His question is, if we keep the if you change the methyl to tertiary would the staggered form acquire some energy? Yes, it will have the basic energy. Okay.
Like we did for ethane, wouldn't we set this as relative 0 energy?
Like we said for methyl, for the tertiary butyl, want to set it to 0. You can, but if there are no other competing interactions, in the case of butane, you will understand it better. Okay, we will have many conformations which will have some energy component coming, with some energy component, and you will see that you will not consider that as 0. The minimum energy is what you would consider it as 0. Okay.
So, but like when it's relative, it makes sense to keep the minimum one as 0, right?
Yeah. So here we keep it as 0.
Yeah, but
Okay, fine. The last.
Yeah.
The last.
Yeah.
Group. Okay, so when we get.
Yeah. So here you will say it as 0, right? So between these two, this will become 0 kilocal per mole. The steric is not playing here once you bring them to a staggered position. Okay. So now how will this curve change? Every rotation with respect to 60 degrees. So 4, let's say 3.3 is here, right? So you start from here, again to touch 0, go up to 3.3. It's not very perfect. Touches 0, again 3.3, and then becomes 0, and then it will go to 3.3. So the variation within the eclipsed conformation is only 0.3, right? So replacing a hydrogen, adding a methyl has raised the barrier for rotation up to 0.3 kilocal per mole. So you can understand every addition that you do it to the basic system, how it is influencing in terms of the rotational barriers. Okay. So torsional, what are the torsional interactions we said? CC-CH interaction 1, CH-CH torsional interactions 1. For CH-CH torsional interaction, we took it as 1. For CC-CH torsional interactions, we took it as 1.3. Right? So let me tie this up as we discussed previously. Okay. So this is a propane. I remove a hydrogen from here. I remove a hydrogen from here. Connect these two ends. Then what do you get? Cyclopropane, whose structure is this, right? If you want to have a three-dimensional view of it, it's flat. I start placing the hydrogen. So each carbon has 2 hydrogens to the structure. Okay. This carbon-carbon bonds does it rotate? We discussed this in the morning. So no rotation possible. So is there any conformational changes possible for this structure? Nothing is possible. Nothing is possible, right? There's no conformational changes possible, right? How many, do you find eclipsing interaction in this compound or not? In cyclopropane, do you find eclipsing interactions? How many eclipsing interactions? 1, 2, 3, then? 6 eclipsing interactions are possible. 1 here, these 2 hydrogens, if you look through this axis, right? If I see through this axis, this 2 hydrogen and this 2 hydrogen are eclipsed. So this is one set, this is another set, 2. Along a carbon-carbon bond, you have 2 eclipsing interactions. Along this carbon-carbon bond, 1 eclipsing interaction, another eclipsing interaction, right? And this carbon-carbon bond behind, right? So you have 1 eclipsing interaction here and another eclipsing interaction. So totally 6 eclipsing interactions possible for simple cyclopropane. Now the question is, how stable is this compound, you think? It is very, very unstable. Due to torsional strains. Is it the torsional strain playing a dominant role, or you have something else also along with the torsional strain? Angular strain is also playing an important role, right? Because each of these carbons are sp3 hybridized, right? It's supposed to possess 109.8 degrees, but what you see here, it's constrained to 60 degrees, right? So both the angular strain along with the torsional strain makes this compound so reactive. It's a high energy compound, you may say, right? But conformational changes are not possible. It just holds that much energy. Any reaction you want to do, just open up and then ready to do that reaction. It's holding that energy that much, right? That's all because of the 6 eclipsing interaction that it has, plus the huge amount of deviation of the tetrahedral bond angle to 60 degrees, which gives it very high reactivity. Okay. So what will be the energy that you can expect? Forget about the angular strain component, right? Based on the eclipsing interactions alone, can you predict how much the energy would be for this compound? 6 eclipsing interactions, all of them are 6 CH eclipsing. So the energy of this compound could be 6 kilocalories.
So should it be more including the angular strain,
It should be more.
but not talking about
It should be more. We have not discussed about angular strain till now, right? So taking into account only the eclipsing strain, which is the torsional strain, you can simply calculate that it is going to be 6 kilocalorie per mole. Plus, of course, corresponding to that coming from the angular strain. Okay. So now we'll go to a 4 carbon skeleton, which is butane. Adding one more methyl to the carbon. Little we are introducing complexity. Okay. So if you have 2 methyls, we can rotate around the central carbon. Say it again. Second and third carbon. First, second and third. Second and third we pay attention to. Look at the second and third carbon because its structure is drawn, so you can analogously you can do that. And now when you are trying with this, or trying to put the methyl, you will put the methyl second carbon is at the front, third carbon is at the back, or maybe second is at the back or third is at the front.
Even methyl at like instead of there, you put at like other hydrogens place, then also it will still get your strength.
Say it again.
The
If-
behind CH3, right?
Yeah, CH3.
Put that instead of either of the behind H, like interchange the position.
You put methyl here.
Yeah, and a hydrogen now. That will also.
Oh yeah, that is also eclipsed.
Right?
That is also eclipsed, yes. Because there, here is methyl eclipsed, there it will be methyl hydrogen eclipsed.
Yeah, twice.
Yeah, you will have that.
But like this is more unstable.
That's why it is placed on the left extreme.
Right.
Okay. So, methyl eclipsing interactions is one point here. Another one is hydrogen eclipsing interactions. As we mentioned, methyl hydrogen eclipsing is also possible upon rotation. So, you have 3 torsions, torsional strain arising in this molecule. Initially, we had only torsional strain, no sterics. And there was only one torsional strain because of CH for ethane. When we came to propane, we had HCH3 scenario alone and CH alone. So, you had 2. Now, you are coming up with 3 possibilities of torsions, right? So, now CH we are familiar, 1. Methyl interaction, methyl CH of course you know 1.3, right? Methyl alone is 4 kilocalorie. Now you can see how much the steric has contributed. Because now both the methyl hydrogens are actually bombarding. Okay? So they are hitting each other. And when it hits, it would rotate, this methyl would rotate. And when it just falls in between one of the methyl, it just passes back. Okay? So you have these motions, but the motions are not as free as it was before in the case of propane and in the case of ethane. Right? So it has to now hit each other and then this methyls have to rotate and then it would pass. So there is some kind of a barrier which is quite significant than the other 2. Is inbuilt in this molecule. So let's write all the conformations. Since he mentioned it, it would be worthwhile to write all the conformations and then figure out how much each one contributes to.
4.0 is. The 4.0 is only that.
Methyl eclipse.
Eclipsing including the study.
Yes. Okay. Including the sterics. So if you, let's say if you rotate this methyl away from this methyl 60 degrees, the second structure would be looking something like this. right? Rotating 60 degrees. What? The methyl. Methyl behind, you have rotated it to 60 degrees. What is the next conformation you can generate?
So basically CH3 is behind the H.
Rotate further 60 degrees, right? Further 60 degrees. So this methyl would eclipse with the hydrogen. When you are rotating the methyl, right, that carbon is attached to these two hydrogens as well. So if you push the methyl, these two hydrogens would also shift. Oh, okay, sorry. Okay, now. So then if you move the methyl, methyl and hydrogens are eclipsed. So methyl, HH, methyl comes here, hydrogen comes here. Yeah.
The second one is that the standard configuration for this. Yeah, because the
It's
angle
not the
will be
one.
more than 60 degrees, right?
Yeah.
Okay.
This is kind of skewed. They call this as a skewed conformation. Okay. So then you will have so methyl comes here now, hydrogen here, hydrogen here. One more 60 degrees, we have not completed the right, staggered, sorry, eclipsed, one more 60 degrees. Methyl comes here, hydrogen comes here, comes here. One more 60 degrees rotation, you would ultimately reach here, right? So this is a whole rotation process the methyl undergoes, right? So in this case, methyl eclipsed, here methyl staggered. We don't call that as a staggered. Conformation wise, it is a skewed conformation. But in skewed conformation, even though methyl is placed between the methyl and the hydrogen, this methyl is placed between the methyl and the hydrogen, you are still seeing the steric effect. So to see a steric effect, one methyl, one hydrogen is not going to be there because it is somewhat in between, right? When you place it like this, methyl and hydrogen will not have the steric effect, but when you have two methyls, you start to see the steric effect coming into picture. So that is in this form called as a Gaussian effect. You must have you're asking about it, right? Gaussian effect when methyls are this particular conformation will have a Gaussian effect. Any other Gaussian effect having conformation you have can you identify here? This one. Yeah, good. So this also has a Gaussian effect. Huh? Though the methyl is placed in between the methyl and hydrogen, it can exhibit the steric effect. Okay? So that is called as the Gaussian effect. So then in this form, you have methyl hydrogen eclipsing. In this form again, methyl placed between two hydrogens as it was in the earlier case, right?
CH3 steric interaction always in stagger.
Yeah, in the adjacent position.
always staggered.
Always staggered, yeah.
So what's the energy that the molecule attains because of the effect? Like,
What is the energy that it is affects? Yeah. So here it is 1, here it is 4 we said. Let's work out the energy now. How much does it amount to? 6 kilocal per mole. So in butane, when methyl is eclipsed, this is the energy you would have. Any other case you see methyl eclipsing? Anywhere else? No, right? This is the only form. Okay, come to this. Hydrogen staggered, 0. Hydrogen staggered between methyl and hydrogen, again 0. Methyl between methyl and hydrogen amounts to 0.9 kilocalorie. Okay, so methyl gauche will lead to 0.9 kilocal per mole. Not so absolute like that, because when methyls are like this, they have a freedom to rotate, right?
If it's 0.9 for CH between CH3 and there are
No.
CH3, so
Here between the hydrogens is 0. Methyl between the hydrogens is 0.
no, like top methyl between left right is 0.9 and this between those is 0.9. 0.9, 0.9.
No.
methyl hydrogen.
Total is still 0.9. Okay.
Total is still 0.9, yeah. So this is 0.9 overall. Here how much do you account for? Methyl hydrogen eclipsing?
Yeah. 1.3.
1.3. 1.3. 1. Here 1. How much does it amount to? 3.6. How about here?
0. That's it.
0 kilocal per mole. So which is of the lowest energy? This one. Do you have similar structures here? Can you identify? This one amounts to how much? Also 3.6. This is again 0.9. So can we modify this curve? If you plotted, how would it look like? It starts with say 5, 6, right? So the highest energy starts from here, which is the eclipsed conformation, right? So then it comes to 0.9. So let's say we make a mark here. And then it goes to 3.6. Right? And then comes back to 0. And then goes to 3.6. Comes to 0.9 again. Goes to again 6. So this is eclipsed, right? This is gauche. This is staggered, 0, right? So this is gauche. Again, this is eclipsed. Okay. So now, what can you conclude from this picture? The highest energy conformation is eclipsed, right? So it cannot stay there because it's of highest energy relatively. And the lowest energy conformation is the staggered, which is this. What is that? This one. Right? This is the lowest energy conformation. So when it comes here, let's say when it achieves this, the difference between this form and this form is not so significant. It's only 0.9 kcal per mole between the staggered and the Gaussian. Right? So it can populate between this and this, crossing over a barrier of crossing over a barrier of 3.3 or 3.6, yeah, but he minus 0.9. So from here, if it has to reach here, that much energy it would have to spend, which is okay at room temperature, right? So it would quickly convert between these two. So in a common population, when you have this butane in a solution, or when you are characterizing it, you will find this and this in major proportions than this. Okay, so a typical ratio would be, let's say, statistically speaking, this is 2 and this is 1. So you can guess the ratios. 66% of this and this with 33% of this one. That is the statistical ratio you will find between the conformers. This is not possible, right? So what you would see often is, you will see mostly this form and this form, which is staggered, and this is Gaussian. Yeah.
So how was it even possible to go to the eclipse form? Because it's like considerably higher.
Yeah, it is very high energy.
So how is the molecule rotating itself?
When it is coming here, when it faces the repulsion, it would just go back. It would make the other route instead of crossing over this, right? Because the barrier is quite significant. It realizes that it is going to face a big, right?
It never crosses.
It may cross if you provide appropriate energy. It can do that, but instead of doing it, it would just take the reverse route. Right, shuttle between this station, but not crossing this, right? So you would have a significant, because you have built in a significant barrier. So just imagine if you are just making it a little bigger, much more bigger size groups, then you are going to basically increase the barrier significantly, and you do not even dare to cross, right? So it would just switch between these two stations, this bypassing that way, right? Bypassing the major groups, getting eclipsed. So that it would avoid, and it would do only this rotation. Okay, so there are various minimum energy pathways you could locate. This is just for butane. You can try that out for like you are mentioning, 1-2 carbons you take. Try that out and see what are the other possibilities that you come up with. Are there any other conformations for that? And how much is the energy that you can account for this? Okay, so that you can try it out. And a quick, I think we have to close because Bala will come. Just a small, just the thought-provoking process. I ask you a few questions. Let's say we have, we started off with ethane, right? We start off with ethane. Let's say you have, you don't have a system where yeah.
In a compound with 2,3,3 tetramethyl butane, so where everything is CH3, will we have the Gaussian with that?
Tetra?
2,2,3,3 tetramethyl butane.
Two more methyl group substitute. Yeah.
Both the second and third
Yeah.
So will we have the Gauss effect since everything is CH3?
Check that, you can check that off. If you have two methyls, let me clean this board a little bit. What's that?
So what is the
If you have this structure, so what he says is if you have two methyls,
So even those two hydrogen atoms are methyl.
Making all of them into methyls.
Everything methyl.
all of the methyls. Okay, all of them methyls. This also is a methyl. So hexamethyl ethane kind of system. Okay, so if you have this, this is again Gaussian only. How many Gaussian effects are you have here? 6. Because this is a Gaussian, this is again a Gaussian. Again you have a Gaussian here, you have a Gaussian here. All of them are Gaussian interactions only, right? So each of these Gaussian interaction would account for 0.9. 6 of that would turn out to be 5.4. So increasing the barrier even for the Gaussian conformer to a significant amount.
Sir, but it won't be 0.9, right, sir? Because you had one CH3 and another H there.
Yeah.
Here they're both are CH3.
It may be a little more, but overall number that you would come up with this, let's say assuming 0.9, you would come up with 5.4, which is relatively higher than what we had seen previously.
So then the staggered form and the Gaussian form will have the same energy.
Yes, absolutely. Okay, because there is no other form for this available. And if it is eclipsed form, each one would contribute to 4 methyl, so 3 of them. So you would have 12 kcal per mole for the eclipsed conformation. Compared to ethane, you have made it 4 times higher. You have boosted the barrier by putting bulky methyls there. And for this particular compound, the carbon-carbon bond length, you will see that it is increased from the defined bond angle of bond length of 1.54. Okay, so greater the size of the substituents, it would stretch even further. Hexaphenyl ethane, all the hydrogens are replaced by phenyl groups. Okay, benzene rings. Place them with benzene rings. You will see the CC bond length is increasing drastically, even if you compare it with simple methyls. Okay. Likewise, a lot of studies are known. Even now, there was a report, the longest bond length, carbon-carbon bond length. They've tried to push it to the highest extreme, which can go up to even 1.81 angstrom. Okay, by designing such sterically bulky substituents and locking them in a particular geometry so that, or pushing them to undergo all this strain, steric and all, how far this bond length could be stretched, they told that it can go up to 1.8. And beyond a point, they feel that there are no 2 electrons in the bond. There are only 1 electron which just in the bond. So there's also a recent paper which came, which talks about just 1 electron bond. It's a Nature paper actually. So all these challenging tasks are being carried out already in the laboratories. You will be interested to know. Okay? Yeah, please.
You mentioned something about
Phenyl benzene.
Yes, sir.
Sorry, hexaphenyl ethane, correct.
Should that be extremely, like, it should be extremely unstable, sir, so it should maybe try to break apart?
True. It would break apart, forming
Like,
triphenyl methyl radicals.
yes, sir.
Because that with large amount of sterics, you're stretching the bond, obviously it is very weak, right? So if you shine it with light, they would homolytically cleave, forming a triphenyl methyl radical, which is very stable.
Yes.
Because this radical can sit around this benzene ring, stabilize itself. It is same like you view the positive charge on the triphenyl methyl carbocation
Yes.
can be delocalized in every part of the ring, right? So similar situation can happen with radicals. Here no ionic mechanism, but you just shine light, the bond cleaves homolytically, gives you the radical, which can be further analyzed.
Also, sir, one 3-part question, sir. Can we also take between CH3, CH2, like the conformal between the first and the second carbon?
Yes.
If that is possible, can you please tell me the values of like CH2, CH3 steric engine, sir, and then
You can assume it to be the same.
assume it to be
Assume it to be the same, like the methyl hydrogen. Methyl hydrogen interaction 1.3 we have, right?
Yes.
Assume it to be that number, then you calculate. See what is the changes you see in terms of
for all
this.
the things, sir. So even if CH2 is between CH3 and H, and even if CH2
Yeah, what you will have is the ethyl sitting between the, right?
We have CH3.
Ethyl will be in place of CH3. That's the only change. So assume ethyl as methyl, and then you do the calculations, because it will be like CH2. CH2 and one is going to be CH3. That particular conformation will have a slightly more energy because they would have more steric interaction, right? But nevertheless, you consider that as a number. 1.3 is what we discussed. Based on that, you work it out. Propane, exactly. It will behave similar to propane. Okay? Yeah. Yeah, so I wanted to tell, this is ethane. This you assume at methylamine. Okay, so methyl you see, the behind circle is for nitrogen atom. 2 hydrogens are there. Nitrogen has a lone pair. In this case, it's an alcohol which is methanol. 3 hydrogens. Behind circle is not carbon now, it is oxygen. Oxygen has 1 hydrogen, OH, and these are the 2 lone pairs. How do you compare the barrier with respect to rotational barrier with respect to ethane for these 2 molecules? Ethane we know for the eclipsed, the high energy conformer is 3. Here it is 3, right? We calculated it as 3 kcal per mole. How about the other 2?
Greater. Yeah.
So
So a little greater than 3.0 and a little, last will be a little greater than that. Like a little greater than a little greater.
but you don't have the bond pair repulsions, right?
Sir, is the sigma 1 repulsion?
So sigma 1 repulsion is absent. 2 of them are absent. In these two cases, 2 of the bond pair repulsions.
Interaction is stronger than a bond pair.
Lone pair repulsion interactions are stronger.
Yeah.
What we studied was the lone pair in the same atom and the bond pair in the same atom.
No, staggered only, but we are talking about the rotation energy barrier. So take the eclipse reconfirmation of this. So barrier for the eclipse conformation of ethane is 3. The eclipse reconfirmation of this, how is it going to be? Eclipse reconfirmation of this is going to be here.
It's going to be higher because bond pair repulsion.
What is the lone pair bond pair we are talking about? We are talking about the torsional strain. Torsional strain. So here you have a bond pair, here you have the lone pair. Through space, how the repulsion is going to be? Through space, how it is going to be?
How will it form an exact, last 2, how will they form an exact eclipse? They won't.
They won't, but see, it will not remain. I'm not saying it is not going. It is going to remain in that form.
Right.
Even for ethane, it is not going to remain in that form. So whenever this bond pair and lone pair comes, how much is the barrier for the rotation? You will see. So CH eclipsing interaction is absent. Here 3 CH. Here 3 CH. torsional interactions, right? Here you will have two CH-CH eclipsing interactions. Here you will have only one CH-CH eclipsing interaction. So how will you grade it? It's going to be 3 means this is going to be 2, this is going to be 1. You go back and check, right? So you will see the net result barrier is going to decrease, not exactly 2, right? But it is certainly going to be less than 3 to close to 1 is what you would see, right? And another point, now we are losing the eclipsing interactions and hence, I think sir is waiting, sir has come. So think about if the distance between the carbon-carbon increases, then how would the repulsion interactions change? Okay, because this is the bond between carbon and carbon. You can also think of interaction between carbon and oxygen, carbon-nitrogen bond length differences, carbon-silicon bond length differences, right? So each one will have the bond length changes. Accordingly, the substituent group will also have a stronger or weaker interaction depending on their proximity, right? So depending on that, you will also have the values different. So it depends on the size, depends on the bond length, right? All of that is going to dictate if your rotation is going to be feasible, less feasible or more feasible. Okay. So I will stop here, then leave you to think over. Branched benzene. Can you give me an example? That means you're talking about sp3CH with sp2. Okay, that's completely a different story.
It doesn't work like this.
It doesn't work like this. It's completely a different story. Again, you will have to draw the Newman and then talk about their interactions. Concept is same, but the way you measure or calculate is going to be different. The magnitude that we are speaking here is not going to be same. So you will have different set of calculations. But you can apply the same concept there also, if you know the exact number. Okay. Okay, in the next lecture, I have 2 lectures on Monday. So when I see you, I will explain as to how this simple concept, which we learned in the undergraduate or probably in the 12th standard level, how it is applied in research, right? And we have tried to solve a problem which was long-standing just through this conformational analysis. Okay, I will give you the lab, in-house example, so that you get a clear idea as to how you can manipulate these interactions.
On the behalf of everyone, I would like to express our heartfelt thanks to Dr. Venkatakrishnan for delivering such an insightful and enriching lecture. The way you presented the topic of confirmation has truly broadened our understanding. Once again, thank you for the astounding lecture and our insight and filling our mind with insightful thoughts. Thank you.
Swayam Prabha, Digital India, Educated India.